Tarini, I forgot to mention to you, the theme, obviously, Galactic Center To and Fro, refers to the fact that we're taking a trip to the Galactic Center, and we're talking about things exploding out of the Galactic Center.
Okay.
And it's our galaxy. All right. I'm just confirming that we're YouTubing. Yeah, we're YouTubing. Okay, so here come the attendees. I'm going to mute myself. We're ready to go.
Okay. Sounds good.
So.
Okay, good morning, everyone. Welcome to the first briefing of June 2nd. My name is Tarini Konchady. I'm the WAS Media Fellow, and I'll be your host for today. WAS Press Officer Rick Feinberg will be handling the Q&A, and the editor of WAS Nova, Susanna Kohler, will be handling the chat, and together they will take care of any technical issues that may crop up during this briefing. Our topic today is Galactic Center To and Fro. We're going to be taking a trip to our Galactic Center and examining it in every which way possible, basically. There will be 4 releases going out with the presentations associated in this briefing. And yesterday's presentations and any associated files are already in the online press kit. So we are recording this briefing and streaming it to YouTube, and a recording will be available later as well. If you haven't been to a briefing before, the way this works is all our speakers present consecutively, and then we have a big grand Q&A session at the end. So because we're doing this virtually, we have a Q&A box where attendees can enter their questions. When you do, please give your affiliation and who you're directing your question to. If you have the same question as someone who's already submitted one, you have the ability to upvote it or comment on it. And all questions will be answered after the speakers have given their presentations. So in order, our speakers today are Christopher Russell of Pontificia Universidad Católica de Chile. His topic is Galactic Center VR. He'll be followed by Joan Schmelz of the University Space Research Association with the talk, The Dominance of the Magnetic Field in the Central 5 Parsecs of the Galaxy. Joan will be followed by Shuo Zhang with Revealing the Powerful Particle Accelerator in the Galactic Center. And rounding us off, we have Andrew Fox of the Space Telescope Science Institute. Forgive me, I forgot to mention, Shuo Zhang is affiliated with Bard College. And Andrew Fox's presentation, the last one, is The Illumination of the Magellanic Stream by an Intense Flash at the Galactic Center. So without further ado, I will hand it to Christopher.
Yeah, that's the right one. And then share down the bottom. Hi, everyone. It's my pleasure to be speaking to you today about Galactic Center VR. This is our outreach app that we developed at Pontificia Universidad Católica de Chile as part of the Instituto de Astrofísica VR lab, though I recently moved back to the US, so I have those other 2 affiliations there. This was a project to immerse the public as much as we can into one of the simulations of the Galactic Center that we've had a good bit of success publicizing. But now we want to see if we can take this even more immersive, and that was our motivation behind Galactic Center VR. Next slide. Just click. Now you can use the next slide. Thank you. All right, so Chandra is an excellent telescope in order to study the Galactic Center due to the Galactic Center being crowded and Chandra having excellent X-ray vision in terms of resolving different structures. So in the composite image on the left, you can see blue X-rays. You also have infrared and yellow and purple. On the right, you have just the X-ray image. At the very center is Sagittarius A star, but there's all these other X-ray sources around. So this is the kind of emission, this diffuse emission that we're trying to model. We had good success with those models, and now those are the exact same things we're going to put into the VR. So rather than show a bunch of slides or text about it, I figured let's just do a live demo. So that'll be what's starting now. I hope this works. It's a little bit risky. All right. So now we are in Galactic Center VR. Here is the supermassive black hole. Sagittarius A star, the black sphere. We did have to blow it up in order to make it visible. It's not actually that large. It's about 10,000 times larger than it should be. If we made it its actual size, it would be a pixel though. Around Sagittarius A star, you have 25 Wolfer A stars. So these are very massive stars, at least initially. And then now they are blowing their outer layers into what are called winds. So if I zoom in onto one of these winds here, you're going to see the star move on this orbit track, spewing its material outwards. Now these winds are going to collide with their other winds, and that's what makes the X-ray emission. This X-ray emission is detected by Chandra. So you can see an example of shocks all over the place. My favorite region is right at the very center. So this star right here, and by the way, this white is the cursor, or my pointer. You can see the star going around, it's the closest. It creates this nice spiral pattern of material falling into the black hole. Though it does get perturbed by streams coming in from other directions. And so what we wanted to do with this is give the user the ability to move absolutely anywhere they want. If you want to go up, down, left, or right, click in any particular direction. You are seeing some time animation. This is a new thing. We're covering 500 years from late 1700s all the way to 2300. And then new as of yesterday, is if you want to turn the thing back, now the supermassive black hole is spewing. We also have a few more, if we go back to the start menu, some of the other options we have, you can pick between how long you want the time evolution to go, what star do you want to see, just all the winds like we showed, or just one of them. We picked 3 of our favorites. You can look at a tutorial to explain kind of what's going on in the beginning. And then there's also the acknowledgments and other stuff that we have there. So I think that's enough for the live demo, given the time. So if we can go back to the presentation, yep, I will skip to the acknowledgement slide. So I do want to thank Balthazar, Jorge, and Miguel. Balthazar and Miguel are undergraduate students who did an excellent job on this project. I also want to thank our funding agencies there, and then we'll just leave the last slide up. Next one. Thank you. Yep, so it's available on Steam, which is a popular gaming site, as well as Viveport. It's for free, both in English and in Spanish. You do need the PC-powered VR headset now. The standalone is coming soon. And we do have my contact information there, as well as the app's own Twitter handle and Facebook page. So given the time, I think that's up. All right, thank you very much. Okay, stop screen share. All right, turning it over to Joan. Thank you.
So good day, everyone. I want to set up an analogy for you. It involves the Earth, the Sun, and the supermassive black hole at the center of the Milky Way. We live on a planet where gravity dominates, but magnetic fields govern the physics of the magnetosphere and ionosphere. We live in a solar system where gravity dominates, but magnetic fields govern the physics of the solar corona and the solar wind. We live in a galaxy where gravity dominates. Could there be regions where the physics is governed by the magnetic field? That's the question that we're here to answer today. If you ask an astronomer if magnetic fields are important to their research, most would probably say no. They use hydrodynamics to explain their results, not magnetohydrodynamics. Hydrodynamics is the study of fluids in motion. It's based on the equations of Newtonian physics. Magnetohydrodynamics is the study of electrically conducting fluids in motion. It couples Newtonian physics and Maxwell's equations. There are good reasons that most astronomers stick to hydrodynamics. One is simply that MHD is harder. There's even an old joke. Whenever I hear the word magnetohydrodynamic, my brain automatically replaces it with magic. But probably more importantly, you have to measure the magnetic field before you can model it. And measuring the magnetic field is challenging in most astrophysically interesting environments. Let me give you a little perspective from recent history. Years ago, I spent a couple summers as an intern at the National Radio Astronomy Observatory. Radio jets were the sexy science of the day, and one of my most vivid memories was not of my own research, but of senior astronomer Alan Bridle saying something like, "Hydrodynamics is just not cutting it. We're gonna have to go to MHD." He said it with both trepidation and gravitas, like it was a decision he had not made lightly. It's the reason I remember it so clearly. A few years later, I moved to solar physics in time to witness the launch of the Yoco Solar Telescope. The movies were so dynamic that they motivated our NASA program officer, Dave Bolin, to publicly retract the results of his own thesis, where he'd modeled the solar corona as a plane parallel atmosphere. So astronomers like Alan and Dave are sometimes confronted with data that are so compelling that they could no longer ignore the role of the magnetic field. This happened years ago for radio jets and solar physics. It's much more recent for star formation and interstellar matter, and other disciplines like galaxies and the Galactic Center are just facing it now. It's very much like stepping off a cliff. Now, I wasn't going to do this for myself, but I'll let my avatar do it for you. We are all very gravocentric creatures, so that first step is quite scary, especially if you're trained from an early age like I was, that gravity is the only force that matters in astronomy. But the magnetic fields will be there to keep you from falling and to support you. That first step is called the plasma beta. It's an easy way to check if magnetic fields are important. Beta is the ratio of the thermal pressure to the magnetic pressure. So if beta is greater than 1, it's called a high beta plasma. The magnetic field may be present, but it doesn't dominate. And a good example is the solar surface, the photosphere. But if beta is less than 1, it's called a low beta plasma, and the magnetic field dominates the physics. A well-known example is the solar corona. It's why beautiful loops like these can form in the solar atmosphere. We said earlier that you have to measure the magnetic field before you can model it. The HAC+ instrument on SOFIA is providing high-quality measurements for astrophysically interesting environments like the Galactic Center. These data give us an opportunity to see the magnetic fields play a significant role in the physics of the region. So the image is an infrared composite of Sagittarius A, the center of the Milky Way. And we're going to add the magnetic field streamlines in the next slide. But remembering that beta is the ratio of the thermal to magnetic pressure, and using values from the literature for the temperature and density, and calculating the magnetic field of 5 milligauss gives us a very low beta, 0.001. The image is the streamlines from HAC+ for the Galactic Center region, and we'll combine the streamlines with the IR composite in the next slide. But observations of the Galactic Center tell us that turbulence is important in this region, and the traditional plasma beta doesn't account for this. So we define beta prime as the ratio of the turbulent to magnetic pressure. And again, using values from the literature, we get beta prime is 0.03. So this image combines the infrared composite and the streamlines for the galactic center. And accounting for turbulence or not, we are in the low beta regime where the magnetic pressure dominates. It tells us that magnetic fields may govern the physics in the regions surrounding the supermassive black hole. And like at the solar corona, the magnetic field may be channeling the plasma. So what does this mean for the physics? Well, let's speculate. There are two long-standing mysteries about the galactic center region. The first is about star formation. Even though there's plenty of raw material, the amount of star formation is significantly less than expected. The second is about activity. Black holes at the center of many galaxies are active, but ours is relatively quiet. The strong magnetic fields could solve both these mysteries. It could suppress star formation, and it could keep the black hole from swallowing the matter it needs to form jets. So let me end with a short video clip. We're starting with the infrared composite of Sagittarius A with no magnetic field streamlines. We're going to slowly darken the streamlines until they actually get too dark. And then somewhere in the middle is the perfect artist's rendering of what we find happening in Cygnus A. So if we go back to our original question, even though we live in a galaxy where the gravity dominates, could the regions near the central black hole, could there be regions where the physics is dominated by the magnetic field? And the answer appears to be yes. Thank you. We'll turn it over to the next speaker.
Hi everyone, I'm Shuo Zhang, and I would like to introduce an intriguing type of sources in the Galactic Center that are the storytellers of powerful particle accelerators in the Galactic Center region. So here we are referring to the central a few hundred parsecs centered on the dynamic center of the Milky Way galaxy. So if you zoom in and take a closer look at this region, the central a few hundred parsec, you'll see very energetic and turbulent phenomena ongoing. Let me start off by showing this amazing picture obtained by the Meerkat Radio Observatory. So the horizontal line shows roughly the position of the galactic plane, and the central supermassive black hole, Sagittarius star, is roughly in the center of this image. So the most striking phenomena that you can see here in this image is the existence of numerous thin and long filamentary structures scattered everywhere. And these filaments can be as long as tens of parsecs and as thin as 0.1 parsec. And what are they and why are they there? Thanks to the radio observations throughout these years, we know that these filaments are tracing the locally enhanced and highly organized magnetic field that aligns with the major axis of these filaments. And then the relativistic particles are the fuse here. They are injected into the filaments, they spiral around the magnetic field lines within the filaments and produce the synchrotron emission that falls into the radio wavelength that are observed here. But the ultimate questions we aim to answer are, where do these extremely relativistic particles come from? And what are the powerful particle accelerators in the galactic center that eventually light up these amazing filamentary structures? So here are our most recent results on the X-ray observation, the Chandra deep X-ray observations also in the Galactic Center region. And such a star is in the lower right corner in this image I'm showing. And we are looking at roughly like 30 parsec within such a star. And so these filaments are also like detectable in the X-ray besides in the radio wavelength. So previously, we know there are roughly like 5 X-ray filaments in this area, but using this recently obtained deep observation, we see the evidence for like 5 additional like newly discovered X-ray filaments here. So the key to have a full picture for this filamentary structure is to like obtain as much as information for the multi-wavelength from the multi-wavelength data, so that using their spatial distribution, spectral information, or even like variability information to extract information for the location and the type of the source that can serve as the powerful particle accelerator in the galactic center. So very recently, we also obtained like new deep observations by NuSTAR, the high energy X-ray space telescope, also focusing on this region, aiming to study these filamentary structures. So here is an example to show the power of a multi-wavelength study on these filaments by combining the X-ray and radio data. The image on the left is the Chandra X-ray image of one specific filament that runs perpendicular to the galactic plane. And the image on the right shows the Meerkat radio image of the same filament overlaid with the Chandra X-ray contour. So it's very clear that both X-ray and radio signals are detected by the filaments. And again, by combining the X-ray and radio information and extract the spectral information, variability information, eventually we can pin down like the location and energy budget for the particle accelerator that powers these filaments. So here I want to use a like cartoon image on the left to show a global mechanism that our team proposed to try to explain where these extremely relativistic electrons come from. So if we have a powerful like a cosmic ray accelerator or particle accelerator in the Galactic Center with such a star as very viable candidate, and this particle accelerator are able to produce hadrons like protons or ions up to TeV or PeV energy range. And these extremely relativistic hadrons can interact with the ISM, including molecular clouds, and produce secondary electrons in the energy range, ranging from like GeV to TeV. And these relativistic electrons are the source that light up these filaments as observed in radio and X-ray bands. And this, we initially proposed this model in our 2014 paper and further illustrated in the paper we just published 2 months ago. And this mechanism is consistent with, I think, the scenario suggested also by the Meerkat, as shown on the image on the right, that there might used to be a very energetic explosion or outburst from the Galactic Center region, driving this bipolar radial bubbles to the north and the south. And then you also see a very clear association with this bipolar radial bubbles with these filaments outlined by the right lines there. So that energetic outburst from the Galactic Center, maybe from Sagittarius star or other sources, can be the driving force for both the bipolar radial bubbles and these filaments. So we think this sort of like global mechanism taking place in the Galactic Center may explain these filaments. Lastly, just want to have a recap for what we have discussed, that in our model, we think the filaments can serve as the probes for powerful particle accelerators in the Galactic Center. And using the Chandra deep observation of the Galactic Center, we are looking at more like new X-ray filaments in the Galactic Center. And we proposed a global mechanism for the filaments where the supermassive black hole is the engine for the powerful, for the particle, for the relativistic particles. Only by like carrying out a systematic multivalent study on filaments, we can like further test this global mechanism in the Galactic Center. That will be all. I'm going to turn it over to the next speaker.
Good morning. My name's Andy Fox from the Space Telescope Science Institute, and I will be talking about the illumination of the Magellanic Stream by an intense flash at the Galactic Center. This is work with Elaine Fraser and others. Now, to get started, I'm going to be presenting evidence today about how an explosion at the Galactic Center that created the Fermi bubbles could also have illuminated the Magellanic Stream at high distance, around 50 kiloparsecs or more, out in the galactic halo. And by doing this, we're seeing new evidence for how feedback from the center of the Milky Way can impact the rest of the galaxy. Now, this is a slide showing the Magellanic Stream. It's a very extended tail of gas stripping out of the large and small Magellanic clouds, the LMC and the SMC, as they orbit around the Milky Way. And the pink emission here, the pink shaded regions show you the Magellanic Stream and the leading arm. What we have been studying with the stream is to take the Hubble Space Telescope and to point this at bright quasars lying behind the stream. Quasars are these bright cores of distant galaxies, where by doing this, we can analyze the light from the quasars and learn about the composition and the conditions of the gas in the stream. We do this using a technique called ultraviolet spectroscopy, and we record the data using Hubble's Cosmic Origin Spectrograph, or COS instrument. So in this technique, we take the light from each quasar and we make careful measurements of how much light there is at different wavelengths. And that reveals the composition of the gas via these so-called absorption lines. And in particular, we're looking at lines of singly ionized carbon, doubly ionized silicon, and triply ionized carbon. What we have focused on in this new study is the alignment of all these different lines from very different ionization states. The singly ionized ions have just had 1 electron removed, but the triply ionized ions have had 3 electrons removed. So by measuring these different ions, we're learning about the conditions in the gas. In particular, we focus on the widths of the different absorption features. These widths give us very, very interesting information about the gas in the stream. What we found was that these widths indicate that the stream had been illuminated by an energetic flash of radiation. And the evidence comes from the alignment of absorption lines of very different ions. We find that the singly ionized, the doubly ionized, and the triply ionized lines all match very closely, so they live in the same gas. And the reason that's important is you need a very energetic burst of high energy radiation to explain this alignment by a process we call photoionization. The gas has to be photoionized by this energetic radiation field to produce this alignment in the ultraviolet absorption lines that we observe with the Hubble telescope. The only known source of radiation which is luminous enough to explain this photoionization pattern and other observations of the Magellanic Stream is a flash at the galactic center, or a so-called Seifert flare. And in this figure, I'm showing an example of the radiation, the ultraviolet radiation density, or the flux of ionizing radiation in the halo of the galaxy. You can see there are 2 bright cones extending away from the center of the galaxy. And the orbit of the Magellanic Stream, which is shown as these dotted black lines, passes through those ionization cones. So the stream feels this ionizing radiation coming out from the center of the galaxy, producing the observed absorption lines that we see in the spectra. This model is supported by other observations, including optical H-alpha emission of bright visible light from the hydrogen atoms below the South Galactic Pole. And the modeling shows that this flare, this Seyfert flare as it's called, would have occurred about 3 or 4 million years ago. What's fascinating is that's exactly the same time scale for the age of the Fermi bubbles. So we think that the event that released this flash of radiation and photoionized the stream was the same event that created the Fermi bubbles, because they are both dated to be several million years old. To show this graphic that the Space Telescope Science Institute has put together, here's the Milky Way. At the top, here are the Fermi bubbles extending above and below the center of the galaxy. Here's this bright ionization cone, like a lighthouse illuminating the stream. And here's the stream as it passes around the galaxy. Now on the next slide, I want to show a video of this. Here, you're going to see the large and the small Magellanic Clouds, these two galaxies in their orbit around the Milky Way. As they orbit around, they lose this tail of gas behind them. That's the Magellanic Stream. It's this giant arc of gas trailing behind the clouds. As the clouds pass through under the center of the galaxy, they become illuminated by this energetic flash, and that's the Seyfert flash. Let me show the video one more time. You can see in the purpley pink color, the ionizing radiation escaping above and below the poles of the galaxy. The Magellanic Clouds, as they orbit around, leave this stream behind them, and that stream is subsequently lit up and ionized by the energetic radiation that emerges from the galactic center. One of the really interesting things about this is that when we look at the galactic center today on a dark night, we're treated to a pretty impressive sight. We can see the dust lanes, we can see all this structure in the Milky Way towards the galactic center. But just imagine what our ancestors 3 or 4 million years ago would have seen when we had hominid ancestors walking around on 2 feet. This Seyfert explosion would have been energetic enough that it would have been a naked eye event. It would have created this luminous glow around the galactic center that would have been visible to observers looking at the galactic center at that point in time. Here we are 3.5 million years later, seeing the fossil evidence for this explosion in the form of the imprint and the halo of our galaxy, the gas far away from the galaxy that has felt the bright ionizing radiation from this Seyfert flare. And on that note, I will end, and I would like to leave up my contact information. This work is based on a paper accepted for publication in the Astrophysical Journal. And the paper is available online on the archive at the website shown here. And NASA has also put out a press release timed with this talk this morning, and that's available as shown on this URL. So at that point, I would like to stop sharing, and thank you very much.
All right, a big thank you to all our speakers. So if all the panelists could turn on their video, we'll jump right into the Q&A, and I will hand things off to Rick.
Hey, thank you very much, Tarini. Thank you to all of you. That was 4 really interesting presentations. So we have this interesting feature within our Q&A, which allows people to upvote questions that they would like to see answered. So the most recent question that came in got upvoted, so I'm going to start with that. It's from Govert Schilling. He's a freelancer in the Netherlands, and the question is for Joan Schmelz. He asks, what future observations might confirm or reject the hypothesis that magnetic fields dominate the physics in the galactic center? And could the same effects, including suppressed star formation and low AGN activity, be observed in other galaxies?
So one of the next step for us is to take this method, the Davis-Chandrasekhar Fermi method, that we use to calculate the strength of the magnetic field to see if it actually applies in these high shear regions near the supermassive black hole. So it's always been one of the tools that astronomers use to calculate the magnetic field in different regions. And it goes back to the 50s of the times of Chandrasekhar. But it's never been updated to or tested under these conditions of high shear. So I think that's one of the next things that our group is looking into to see if that makes a difference, because that is definitely one of the things that this result is based on. Another independent sort of set of observations that we have to look at with this are Zeeman effects from the Galactic Center, and they compare very favorably for the results of this region. So those are some of the next steps. And other galaxies, so the Hawk Plus instrument does indeed look at other galaxies, and some of the images that I showed in that little montage are of other galaxies. We haven't gotten into the Galactic Center, but because of the resolution, because of how far away they are.
Okay, thank you very much, Joan. So the next question is from Jim Schweitzer. He is from Science Communications Consultants. And I think this question, he didn't say, but I think it's for Chris, because he asks, can you put scale grids or frames around the visuals so you can see how big the objects are that you're looking at?
Sure, you could. I mean, this is rendered from your perspective, so everything you see is angular, right? You're looking out. The whole simulation covers about 1 parsec across, so 3 light years. And I didn't show it in the talk, but on the bottom of the controllers, you can actually see like how far you are from this one. Oh, there you go. So it does actually tell you where you are in relation to the black hole as you move. So we added that little feature there, how fast you're going and where you're located. But yeah, so the whole thing is about a parsec across three light years.
Excellent. Okay, thank you. This next question is from Pamela Gay at Astronomy Cast and Daily Space, and it's also for Chris. She asks, can you see things changing over time in virtual reality or only fly through a static setup? And yeah, if you can see them change, can you show us that?
Yeah, so hopefully this is going fast enough now where you can actually see it. I don't know what the lag is.
Yeah, we see things. We see the stars.
I'm just looking at one particular spot, and I'm not actually moving, but hopefully this goes. And so yeah, it evolves in 500 years of time evolution. And then while it's doing that, you can also move in any direction you want. So yeah, you have 500 years. If you have a lower spec computer, you can do a 100-year option. So hopefully everybody can have a fun animation experience. But we do have the time evolution in there.
Okay, very good, thank you. So the next question is from Martin Ratcliffe. He's a freelancer. It's for Shuo. Could you monitor bursts from the central black hole and see corresponding fluctuations in the emission from the filaments? Such correlated fluctuations would confirm your model and give a precise distance measurement to the galactic center when the time delay between the burst and the filament are set. When the time, I guess from the time delay between the burst and the filament. Are such long-term monitoring observations possible?
Thanks to Martin for these great questions. Yeah, I can answer it from like 2 aspects. Firstly, indeed, we are monitoring the outbursts from the central supermassive black hole, such as star, including the current like flaring events, and also the outburst events in the past few hundred years. But I have to point out that we have all the evidence pointing to that such a star nowadays. So it's like very like inactive. It's actually one of the least active supermassive black holes known to us. So might not be like energetic enough to produce the extremely relativistic particles that are required by the filaments. However, these relativistic particles could be produced by a past outburst from such a star, maybe even like a million years ago. That could maybe also give rise to other for example the Fermi bubbles, and maybe also drives at radio bubbles. So I'm saying what I'm saying is that the time delays between the outburst from such a star and the lighting up of these filaments can be huge, because those energetic like hadrons produced maybe by such a star can diffuse within the galactic center regions, and they can exist there for a very, very long time. On the other hand, as you said, that we are also like closely monitoring any variability from these filaments. Right now, we haven't seen any evidence for obvious change in the luminosity of these filaments, but if you see any thing that pointing to such variability, we'll definitely check out the variability of such a star in the corresponding timescale to see whether we see any correlations. That's a very good question. Thank you.
Okay, thanks a lot. So the next question, back to Gobert Schilling, freelance from the Netherlands. This one's for Andy Fox. He asks, what exactly is new here with respect to an earlier publication by Josh Bland Hawthorne et al.?
Okay, thank you. So what's new here is this is the first time we've looked closely at what we call the kinematics of the absorption in the Magellanic Stream. So we look at how well aligned the various absorbers are in velocity. In the earlier publication that question referred to, that looked at the strength of the absorption, how much absorption was happening. Here we've measured the velocities, and those velocities tell us which models can be ruled in and which models can be ruled out. And it's based on those velocities, which is presented here for the first time, that we can really say that the photoionization model, where there was a flash of radiation which illuminated the stream, is most consistent with the data. So it's based on this new analysis that comes from a very careful inspection of the Hubble cosmic origin spectrograph data and looking at those kinematic profiles.
Okay, great. Well, Andrew, you've got a couple more questions coming your way. This next one is from Leo Enright with Irish Television. The event you described, did it have implications for habitable planets out of plane in the galaxy or in the Magellanic Clouds?
That's a great question. And we think, yes, it did, particularly in the Milky Way, because this ionization cone, this region of intense radiation coming out from the center, would have contained a lot of UV radiation. And we know that if you don't have ozone, you can be in danger from UV radiation on a habitable planet like the Earth. And some rough calculations show that if you're within about a kiloparsec of the explosion, your ozone layer would be totally wiped out. You would not have a chance of surviving. So you would not want to be on a planet in that inner region of the Milky Way, that inner kiloparsecs, which is about 3,000 light years or so, because the UV radiation would have been so intense that that would have been a real threat to your well-being. Now, if you're out at the Magellanic Clouds, I think that's okay because that's far enough away that the impact is not so severe. But it's really in our own galaxy, in that inner portion of the halo, that this is something that you would need to worry about.
Okay, terrific. Thank you. And another question for you, this one from Jennifer Wiseman at NASA Goddard. She asks, have a series of these Seyfert flashes affected the Magellanic Stream or only one flash?
Yeah, so that's another great question. So there could have been a series. We can't rule that out. But what we've seen is that the timescales work for the most recent one. So the age of the Seyfert flash is about a few million years, as I've shown. That comes from the modeling, and that's what you would expect from the light travel time to the Magellanic Clouds, and then the time for the gas to recombine once it's been ionized. So we have evidence for one flash. That's the one that we can discuss in the paper, but we can't rule out that the same thing would have happened before. And looking at other galaxies, this type of activity at galactic centers, the so-called AGN activity, is a very well-known and well-studied type of event. And there's no reason our Milky Way should be any different. So I think it's quite likely that these type of outbursts have happened before. We're just now seeing the evidence for the most recent one.
Okay, and another question for you has come in. This one is from Stephen Lawrence at Hofstra University. He asks, could the Sagittarius star flash be used to obtain distances to infalling high velocity clouds seen in neutral hydrogen radio data?
Yes, that's an interesting thought. I think you could constrain the distances to those high velocity clouds if you knew how intense the flash was. So if you have a good model for how intense that burst was, and we think we now have that, you could use that to calibrate the distances to those clouds. So it would take a little work to pull it out, but yes, I think you could do that. Good idea.
Right, well, it looks like that exhausts the questions in the queue. So unless another one comes in right away, I think we're finished. Unless there's any questions from any of the panelists for each other. I actually have a quick question for Chris, which is, I don't think you mentioned it. How much do these VR headsets typically cost? If I wanted to go to one of those sites and order one.
So they, the range that you plug into your PC, the PC-based ones, they go anywhere from 300 to 1,000. But the main thing is you need a gaming computer. So you have to have that is the more expensive component necessary for this. The standalone version that we hope to have out soon, that's just in the 200 range to 400 range altogether. It won't have as much computing power. You won't be able to do 500 years, for example. You can do a few hundred. But yeah, the gaming computer is what costs you.
So if you've already got the gaming computer, a ticket to the Galactic Center costs about the same as a ticket across the country on an airplane.
Mm-hmm.
Okay.
Yeah, right. So you can. That's a good point. Travel to the Galactic Center for deeper than going across the world.
Okay, great. I don't have any other questions.
I had a question for Joan, if I may.
Please.
These magnetic fields at the Galactic Center are great. It's interesting to see how strong they are. Do we have good models for what created those magnetic fields, where they could have come from?
I think one of the things in my talk is that one of the lines is you have to measure the magnetic field before you can model it. So I think for the Galactic Center region, certainly what we used to do is ignore it. So now we can see it and now we can measure it. So our next step would be to model it. So, and where does it come from? Is it I think it's the old, the same question about the magnetic field in the galaxy. Is it primordial or did it come from somewhere else? Or is it just twisted and turned as a result of the shear of the differential rotation in the galaxy? So I think it's all, the first step, I think the plasma beta, we call that the first step. That one's easy because it's a simple calculation once you have the values. The next step is much more difficult. So modeling the field, I think we take all the MHD type science and modeling that has been done in heliophysics for years. And now we begin to apply it to other environments. And that's what we're starting to do as well. So please stay tuned.
I should point out too that tomorrow morning's briefing, Mysteries of the Milky Way, will have some additional talks relevant to outbursts and the Fermi bubbles. So everybody should come back for that one tomorrow morning. All right, Tarini, back over to you. Oh wait, sorry.
One more question, yeah.
One more question came in. All right. This one back to Leo Enright from Irish TV. I've always wondered if active galactic nuclei might explain Fermi's paradox, like putting a galaxy into a microwave on high for a year or two. Is that realistic? I guess he's asking Andrew probably, but anybody might want to weigh in. Fermi's paradox, of course, being that we don't see any evidence of extraterrestrials.
Well, if anyone else wants to weigh in on that one, they would be very welcome to. The active galactic nuclei are certainly very powerful, certainly visible for very to large distances and high redshifts. It's not so clear how we would relate that to Fermi's paradox, but if others have ideas of how to do that, please go ahead.
I guess we're all similarly flummoxed. Okay, back to you, Tarini.
Thank you, Rick. And I guess, yes, thank you to everyone, to our speakers, the audience, to the public information officers who helped with the press releases and briefing prep, and to Rick and Susanna for handling the Q&A and the chat. The next press briefing of the day will be at 3 p.m. Eastern Time. It's going to be hosted by Susanna. And the topic is planets, exoplanets, and brown dwarfs. Hope to see you all there. And thanks for dropping by and watching.